and also to thank you for the wonderful postdocs. That's my experience. And I'm going to introduce Karen Muller, who is going to give a talk on adaptation to cluster algebraic geometry.
Thank you so much, Anna. And thank you guys for inviting me. I honestly can't say how honored I am to be here in such a beautiful place, celebrating one of my favorite people. So what I'd like to do with the time given to me is talk about something that is also near and dear to my heart. So I'm a cluster algebraist by trade, and while cluster algebras are commutative algebras, the kinds of phenomena that occur and the kinds of questions we ask tend to be a little bit different than the ones studied by most commutative algebra and algebraic geometry. So what I thought I'd do with the hour I have is to give just kind of a whirlwind survey of the quirks that arise in the geometry of cluster algebras and why I find them so exciting. We'll start at what is arguably the hardest part. What is a cluster algebra? So the cluster algebras are weird because they're the output of a construction that involves a bunch of steps, all of which are pretty simple and all of which are pretty unmotivated. So if you're willing to just listen to someone, such as myself, tell you to do all of these things, and then you get an algebra at the end, you can build them, but this is a far cry from understanding why you might care. So one of my goals for this talk is to sort of retroactively justify why this construction you might be interested in with some of the phenomena that arise, some of the interesting results. Okay? And we'll try to motivate this with some examples of very example-oriented. So let's start with how you construct a cluster algebra. So I'll consider cluster algebras defined by quivers, by which I mean directed graphs. And the specific directed graphs I consider won't have loops or 2 cycles. Let's start with a very simple quiver. That's just got 3 dots and 2 arrows between them. It's a path quiver. And the first thing I want to do is I want to label the vertices with variables that are just formal variables, x1 through xn. So now each vertex has become a circle with a function in it. And now here's the tricky part. I want to consider all possible sequences of mutations of this quiver, an operation I'm going to define on the next slide, which is going to piece by piece replace one of the functions, one of these labels with a new rational function in these 3 variables. And it's going to modify the quiver in some way. Okay? But the point is, I'm going to consider not just all the ways to mutate, but all the ways to keep mutating. Okay? And so this will give me some potentially infinite tree of all possible mutations, which we labeled with a potentially infinite set of rational functions called cluster variables. And I'm going to consider the subalgebra of the field of rational functions over Q generated by those rational functions and call it the cluster algebra. Okay, so now we see the anatomy of the definition, but we're of course missing the key piece, mutation. So here's a definition of mutation. There's 4 steps, and they don't commute, but you can kind of rearrange them without much difficulty. But I think this is best demonstrated with an example. So let's mutate the quiver we started with a couple of times and see what we get. So let's start with this middle vertex here. We're going to mutate at this vertex, which means we're going to replace this function by something else and modify the quiver slightly. So let's start by replacing the function. We're going to replace this with the product of the upstream functions, which in this case is just x1, plus the product of the downstream functions, which in this case is just x3, divided by the function we're replacing. Okay? Rational function, not so bad. It's pretty straightforward. And then for now, we'll just copy the quiver down. So next up, we're going to modify this quiver a bunch, and we get this. So now I've got 3 steps which just mess with the quiver. So let's go through them in turn. The first thing I'm going to do here is I'm going to reverse the orientation of every arrow that touches the vertex I mutated at, which in this case is all of them. Then I'm going to add every arrow for a composition through the vertex I'm mutating at, by which I mean a pair consisting of an arrow coming in and an arrow going out, right? If these were functions, it would be a composition of functions, a composable pair of functions. So we have an arrow going in and an arrow coming out. So I add, oh, I got this in the wrong order. Sorry. If I call them compositions, these guys need to be in the opposite order. Because what I need is this arrow this way. If I did it before I added them, that would be the composition. So it's wrong as written, but I want to add the opposites of the compositions the way I've done it. Okay, But however we do it, we add an arrow for every composable pair through the vertex at which we are mutating. And then it's possible that adding arrows can create some two cycles, some oriented two cycles, which we're not allowed to have. So the last step is cleanup. We just cancel them in pairs. Okay. All right. So that gives us one mutation, but we don't just consider one mutation. We consider all possible sequences of mutations. Okay. So let's do it again. Now, if you're particularly, if you are so desire, you can mutate again at the middle vertex, this vertex here. But a funny thing happens. This process, at least if I've done it correctly, reverses itself. You get back to where you started, okay? Which is nice, because it means this process never loses any information. You can always get home again by just undoing the sequence of mutations you did. Okay? But of course, that doesn't give us anything new. We want new stuff. So let's mutate at the first vertex, okay? So we're going to replace this vertex, this label, by an expression involving the other functions. And unfortunately, it's going to get pretty big. So let's for now call it f. And then let's write f over here, big.
Sorry, I have a quick question.
Yeah, please.
When I have a cycle, is everything upstream and everything downstream?
This is just one step upstream and one step downstream.
Oh,
yeah. Yes. Equivalently, it's the product over all incoming arrows and the product over all outgoing arrows. Yep. Good question. And we're yes.
Sorry, since there was a question, I just want to. When you cancel a two cycle, how do you decide which one?
So if I have a bunch of arrows this way and a bunch of arrows this way, the individual arrows don't matter. I just subtract the number of arrows each way until. So if I had 3 arrows this way and 2 arrows this way, I'd be left with 1 arrow this way.
But then couldn't it change getting back to the original one? Which one you were?
It doesn't.
Oh.
Yeah. Yes. Good question. But yes, I think if you write it down, that will not.
Okay.
That will not create an issue. But and I think for the reason that you only create 2 cycles that are not adjacent to the vertex at which you're mutating.
Oh, okay.
So you can go back and forth and weird stuff is happening away, but you don't care. So that's the reason why it's true. Okay, so we're taking the product of the variables upstream, which is this new guy, x1 plus x3 over x2. The product plus the product of the downstream variables, which is x3, divided by the original guy. Now we can do a little bit of cleanup. Put everybody over a common denominator. And we get this. Not too bad. Okay, now let's copy down the rest of our quiver with labels, taking care not to accidentally change any of the indices. And then I'm going to do these in the opposite order, just because the way I've written it is wrong. Yeah. So first I'll add the compositions through the vertex we're mutating. So I've got an incoming here and an outgoing here. So I add an arrow this way, creating a 2 cycle. We'll worry about that later. Now I reverse all the incident arrows. And now I cancel the 2 cycles. And we get following. Okay. And so you can keep doing this. Okay. And if you did, well, one, it would take a lot of time, but a lot of magical things would happen, some of which we'll talk about today. Okay. So one thing that's magical about this guy is we only ever get 9 expressions that occur. No matter how weird your sequence of mutations occur, we will only ever get 9 cluster variables, 9 things that appear. Some other phenomena that occur is the functions are not just rational functions, which is clear from the definition, but they're in fact what are called Laurent polynomials. They're always a monomial over a monomial. Okay? An equivalent definition is they're polynomials where negative exponents are allowed. Okay? That actually is a very strong condition. Let's talk through here. Maybe let's start to mutate at this middle vertex. Let's just do the first step. Let's see what would happen if we mutate at this middle vertex. We get a new guy, which we'll call G. And G is going to be the product of the upstream, which is F. And let me copy that down. Plus the product of all the downstream labels. There's none, so an empty product is 1. divided by the thing we're replacing, which is this. So if I clean that up, I get something that at first blush does not appear to be a Laurent polynomial, right? It's got this guy here. What have I missed out? Yes, perfect. This guy comes down and cancels this. Here and next to here.
X1 plus x3.
Was that?
X1 plus x3 in the denominator.
Thank you. Yes, that's important. Because then you check, oh wait, x1 plus x3 divides the numerator. And we get 1 plus x2 over x1. So mutation had no reason to give us a proper Laurent monomial, but everything magically canceled to get rid of this polynomial in the denominator, and we get back to a Laurent polynomial. This always happens. That's the first sign something cool is occurring. Okay, let's proceed on. Important takeaways, you don't need to know what a cluster algebra is now, you just have to know kind of what a cluster algebra feels like for the rest of the talk. Okay, so some terminology, as I said, functions that appear are called cluster variables. So in the example we just saw, there are 9 possible cluster variables. We constructed, I think, 6 of them, and there are 3 more, and then no matter what, you just keep getting redundancies. Okay? Another important term is a cluster. A cluster is a set of functions that appear together in one of these quivers. So this is a cluster, this is a cluster, and so on. Okay? Here there are 14 clusters, which of course necessarily each consist of 3 cluster variables, because none of the steps change the number of vertices of my quiver. All right. So this example is misleading in one essential way, which is that we magically saw that we only ever had finite expressions that occur. This is misleadingly nice. Most cluster algebras, even the good ones, have infinitely many cluster variables. Just the way life is. In fact, it's so special and rare to have finitely many cluster variables that one of the first results by cluster algebras was classifying those that are finite type. That is, have finitely many cluster variables. Okay. So Fomin and Zelevinsky, the progenitors of cluster algebras, proved that you only ever have finitely many clusters if you're an oriented Dingin diagram. Okay. That's not a lot of options. That's a very small number of quivers, even among quivers with no cycles. Forgot about the delay. So this might lead you to believe, okay, we've got an infinite number of cluster variables. We're looking at the subalgebra they generate of the field of rational functions. So this means, I guess, we're looking at infinitely generated algebras. Not necessarily. Despite this, many of the best cluster algebras are still finitely generated, even though they have infinitely many cluster algebras. You have some infinite generating set, but it turns out most of them are redundant. Okay. So here's an example, due to Bernstein, Fomin, and Zelevinsky. If your quiver has no directed cycles, which is a much broader class than oriented Dingin diagrams, then your cluster algebra suffices to be generated by the initial cluster, and then all the guys you get by mutating one step from that initial cluster. So that only gets you 2n generators, certainly finite, even though there may be infinitely many off in the deep depths of mutation. Okay. This presentation comes with a nice set of relations. So this is generally a very easy presentation to study from the perspective of properties and presentations and whatnot. So acyclic cluster algebras tend to be very nice. An idea we'll come back to later. At this point, in maybe 2005, you're one of Fomin and Zelevinsky. You said maybe every cluster algebra is great. You've proven a bunch of great ones. So you have to come up with, you ask, are any cluster algebras bad in some sense? Okay. And the go-to example for bad phenomena in cluster algebras is what's called the Markov cluster algebra. It's related to Markov triples in Diophantine geometry, but it's just 3 vertices and double arrows in a cycle. Okay. A lot of cool stuff about this cluster algebra, but from the perspective of an algebra, absolutely horrible. It of course has infinitely many cluster variables because it is not an oriented Dingin diagram, but more so, it cannot be generated by any proper subset. This big infinite set of cluster variables, every single one is essential. Okay. So we see that this is infinitely generated, and in fact, worse, it's non-Noetherian. Okay. There are quite a few bad properties of this algebra, so they exist. Okay. And right away, we see a curious phenomenon in the theory, which is that some cluster algebras are quite nice, and we'll see that there are many more quite nice cluster algebras. Why we study them? But if you just draw a quiver at random, it's possible you end up with an arbitrarily horrible algebra. Among horrible cluster algebras, the Markov is actually quite nice. It gets real bad real fast. Yes.
If I have like a quiver with the Markov subquiver, with the Markov quiver as a subquiver, does that automatically translate into bad properties for my algebra, or it's more?
Basically, yes. Like, I'm trying to think what I should say precisely. Actually, yes. I believe what'll happen is if you have a Markov subquiver, you can always look at that algebra and specialize all the other vertices, the other variables, to 1. And that, it should recover the Markov cluster algebra. And so you should be getting a quotient that is infinitely generated. So of course you aren't infinitely generated. There's some tiny details to that I'm worried about, but we'll say the first order, that's my answer. Yeah. Okay. So yes, cluster algebras can be good or bad, but I promised you that we'd be looking at cluster algebras through the lens of geometry. And so let's start attaching geometric objects to these. Now, of course, we'd like to consider the variety associated with this, but from a purely nomenclative perspective, these could be infinitely generated, so we can't just talk about the variety of k-points, right? So I'll do a bit of a hack, right? The big hammer, of course, would be to look at spec of a cluster algebra, but I'm particularly interested in the sets of k-points over various fields. And if I look at the set of k-points of an affine scheme, that's just the ring homomorphisms to k. Okay, so we'll sort of cut to the chase and define the cluster variety of cluster algebra A over field K to be just a set of ring homomorphisms from A to K. Okay. Now, if A is finally generated and K is algebraically closed, this is straight up just the affine variety associated to the ring K tensored with A. Okay. However, this does a better job of handling the infinite case. We can still make sense of Zariski topology and regular morphisms and whatnot. Really implicitly, I'm working upstairs in the scheme, but I'm looking at the k points to sort of have something physical to play around with. Okay. All right. Part of the reason that we're so interested in cluster varieties is because many things you already care about are cluster varieties. One of the early motivations for cluster algebras is how many interesting varieties had a cluster structure in their coordinate. Okay. So here's an example: semi-simple complex Lie groups, Grassmannians, flag varieties, positroid varieties, which are strata inside a Grassmann, decorated type Muller spaces. There's a little bit of fine print there. But generally, we have a large family of interesting spaces that have a cluster structure. Okay. And I've got some fine print here. In almost all of these examples, something a little bit subtle happens. It's not that these are cluster varieties. Rather, they all have an open and dense subset that is a cluster variety, which extends to a stratification of that space, whose strata are all cluster varieties. For example, a semi-simple Lie group has what's called the double Bruja stratification. It is a big open and dense subset, which is a cluster variety, which we often call the cluster variety of that group. But then there's smaller pieces as well that are themselves cluster varieties. So there's quite a bit more structure here in terms of what we mean when we say there's a cluster structure here. But this sort of is our first entry point. Why we care about the structure? Because it appears in all of these contexts. And actually, the more important thing isn't just this variety. As we'll see, cluster varieties can often be quite boring just as a variety. The important thing is it has this family of distinguished functions, the cluster variables, that allow us to ask questions that wouldn't make sense over just any old variety. In these cases, the cluster variables often corresponded to notable functions we already had names for. Right, so in the Grassmannians, we had Blucher coordinates. Turns out those are some, but not all, of the cluster variables. In type Muller space, we have lambda lights, etc. So this allowed us to axiomatize and generalize these special functions on all of these nice spaces. So that's the kind of thing we're talking about. We're looking at interesting varieties that have distinguished functions. So, okay, now let's get into it. I'm going to survey a bunch of interesting results about cluster algebras and translate them into geometric results and see what that tells us about these varieties. So let's start with the first one, quite literally, the Laurent phenomenon. This is just what I've already observed. that we always get a Laurent polynomial. Okay. So every cluster variable is a Laurent polynomial, that is an element in the Laurent ring. In fact, I'm seeing in something slightly stronger, it's a Laurent polynomial with integer coefficients. So it lives inside here. But if every cluster variable is in this ring, the subalgebra they generate is also in that ring. So we get that the cluster algebras contain not just in the field of rational functions, but in fact in this Laurent ring, a much smaller and more tractable ring. Excuse me. But we can make this even richer, right? A is contained inside this Laurent ring, but A by construction contains this cluster here. So if I localize A at these variables, I get the entire Laurent ring. So we see that in fact the Laurent ring is a localization of a cluster algebra. So if you localize a cluster algebra at this initial cluster, you get the Laurent ring in that cluster. Okay. Well, geometrically, what does this mean? We know what localization corresponds to geometrically. It corresponds to an open set where those variables don't vanish. So this says that the open and dense subset of the cluster variety on which the cluster variables do not vanish is isomorphic to, well, the variety of points of the Laurent ring. But the variety of points of the Laurent ring is just an algebraic torus that has n many copies of the field minus 0. Okay. All right. So we see that whatever this cluster variety is, it contains an open and dense algebraic torus. So it's like rational and stuff. So this already says we're in a very nice class of varieties, at least from the perspective of usual algebraic geometry. So let's see a picture. We've got an example going, but it's a little too big. This is necessarily a three-dimensional variety. If we go one dimension down, we have a chance to kind of draw it on a slide. So let's work with the cluster algebra of just this two-vertex quiver. Okay? Just two vertices and a single arrow between them. This is sort of the bread and butter example. It's very easy to work with. If you mutate it a bunch, you'll see that this still has finely many cluster variables. After all, it's an oriented A2 Dinkin diagram. And the 5 cluster variables are these guys here. Okay. So I'm now looking at the subalgebra of rational functions generated by these 5 guys, and I want to say anything about the geometry of those guys. Okay. So we can start with the part that the Laurent phenomenon tells us about, the torus, right? The algebraic torus. So the real points, which we'll draw because they fit on a slide, are the cluster torus here is just a copy of the plane minus the axes, right? A two-dimensional real algebraic torus. Okay. And so it looks like this, a relatively simple picture of the plane minus an algebraic torus, or minus the axes. So what are we missing, right? That was supposed to be an open and dense subset of the cluster variety. But in this case, it's actually quite easy to figure out what we need to add using tools that should already be familiar to you. So here's a construction which is more or less due to gross Hackney Kiel. So go back to the original plane with the axes in it and blow up these 2 points. Okay. So we pick up an exceptional divisor there. Now I've got the strict transform of the axes upstairs, and I just cut those out. And I'm left with the original plane minus the axes, together with the 2 exceptional divisors minus a point. Okay. And it turns out that variety is the cluster variety, or is isomorphic to the cluster variety of that 2-step quiver. Okay. So there we go. There's our first cluster variety. And so while this is a particularly simple space as far as algebraic geometry goes, what I'd like to do, sort of my goal for this talk, is to convince you that the extra structure of those cluster variables gives us more interesting structure here, more interesting questions to ask. So we'll try to make this picture interesting. The first thing I'll notice is that there's nothing special about the initial cluster, right? So our construction was very focused on that initial cluster, x1, x2, x3, right? Like we generate our cluster algebra inside rational functions here. But if I pick any other cluster and change variables to make that guy the initial cluster, I get the exact same algebra, right? So here I make it precise. If I pick any cluster with quiver q prime, there's an isomorphism of cluster algebras that takes the initial cluster in this guy to the cluster I picked here. So this just says there's nothing privileged about the cluster I started with other than the notation I'm using, right? So in particular, the Laurent phenomenon is not unique to the initial cluster. It's true about every cluster, which is to say every cluster variable can be written as a Laurent polynomial in every cluster, okay? That's a lot of expressions. And then we chase it down, we get another localization that's also equal to a Laurent ring. And we also get another open and dense subset of our cluster variety, which is isomorphic to an algebraic torus. Okay? So we see that cluster varieties are filled with a bunch, usually infinitely many, distinguished algebraic tori, which we call cluster tori. Okay? So what does this look like in our example? Well, this example just has 5 clusters, and so it has 5 cluster tori, which I can map in by these 5 maps. So this is the one we started with. Just take this plane minus the axes and map it in here according to this map. But I also have a bunch of other maps, each of which will miss some of the plane, but will hit some of those exceptional divisors. Okay? And so in this way, we're packing 5 different algebraic tori into this space. And then here's an exercise for the viewer. These completely cover the cluster variety. There are no points in this cluster variety not covered by one of these 5 tori. Okay? So that's nice. That tells us a lot of stuff. I mean, obviously, this was already a pretty simple variety. But if we didn't already know that this was non-singular, now we do, right? Because it has every local property that an algebraic torus does. So if this is always true, if a cluster algebra is always covered by its cluster tori, then we're looking at something that is locally as nice as an algebraic torus. Fortunately, this is false. The cluster tori do not always cover the cluster algebra, or the cluster variety. We already have an example staring us in the face. If we took a path of length 3, we get a 3-dimensional variety with 14 cluster tori in there, and they hit everything except one point. And to make things worse, that point is a singularity. So we see that cluster varieties need not always be smooth. But any points, the singularities they have can't be in any of these cluster tori. So, okay, so maybe at this point in the story, we're like, all right, what could happen? What could the cluster tori miss? So let's give these guys a name. A point that is not in any cluster torus is called a deep point, right? Sort of implicitly, the cluster tori are the shallows of the cluster variety, and the deep stuff is the stuff that we can't quite see without thinking more carefully. And of course, any bad behavior like a singularity in the cluster variety must be in the cluster torus because the algebraic tori are so nice. They never betray us by having a singularity. So if you're inventing the field, you're like, all right, let's understand the deep points. Let's figure out what they can look like. And so only recently have there been systematic studies of deep points, which might seem weird because the field's about 25 years old. Me and grad student James Baer classified deep points in finite type and Fermat surface cluster algebras, those with decorated type Muller space. And then another group, Casanova, Gorski, Simmental, and Spire, did it for pository varieties. And not to besmirch all of these lovely people, which include myself, but I would say the main takeaway from these results is that the deep points are too unpredictable to be to be a useful tool for studying the rest of the cluster algebra. To give an example that illustrates that, we saw a path of length 2, no deep points. A path of length 3, 1 deep point. You could say, oh, well, if I have a path of arbitrary length, how many deep points? The answer is none unless n is 3 mod 4, or n is 1 mod 4 and the characteristic is 2, in which case there's a unique deep point. Okay. So even in this is absolutely the simplest family. This is the homework problem 1 in your introduction to cluster algebras course, is studying this family of cluster algebras. And yet even these have unpredictably oscillatory deep points. Even the question of whether deep points exist is non-trivial. Okay. So this says if we want to study cluster algebras, we want to show how bad cluster algebras can be, it's impractical to first classify all the deep points and then study them directly. We're going to have to be a little cleverer.
So do you know anything about the codimension of the set of deep points?
That is a great question. Everybody expects it to be at least 2. Yes. No, yes. For general cluster algebras, I don't believe that is known. Yeah. That's quite tricky, actually. Okay. But let's try a different tack. Okay. So implicitly, what we were just doing is we were trying to show cluster varieties were simple by covering them in these tori, right? Tori are nice, but we couldn't do it, right? It was even hard to figure out when we were succeeding. So instead of trying to cover a cluster variety with algebraic tori, let's instead try to cover it with simpler cluster varieties. Okay. So we can pick a class of cluster algebras that are particularly nice, and then maybe try to cover a cluster variety with just those cluster varieties. And then we'll know that that cluster, that the properties of acyclic cluster algebras will lift up to the one we cover by these acyclic cluster varieties. This leads to the following definition of locally acyclic cluster algebras. This definition is a weird marriage of algebra and geometry. And there's some fine print I'm sweeping under the rug, but the definition is essentially a cluster algebra is locally acyclic if it has a family of localizations that are each isomorphic to acyclic cluster algebras and whose cluster varieties collectively cover the original cluster variety. Okay. So the extreme case of this is if I take a cluster and I localize that entire cluster, I'm getting an algebraic torus, which is kind of degenerate cluster variety. And so if I had no D points, I would be locally acyclic just because I've been covered by these kind of trivial algebraic tori, which are degenerate cluster varieties. Okay? But this is a far more robust definition that, as we'll see, doesn't have this weird phenomenon where it's very hard to predict what is locally acyclic. In fact, lots of things are locally acyclic. Okay. So here, let's start with first properties. As I said, a locally acyclic cluster algebra inherits any local property that an acyclic cluster algebra has. But we've got presentations of acyclic cluster algebras staring us in the face, so we can just study those directly. So we get things like finitely generated, normal, and locally complete intersection. Okay? These are just for free. But this is only useful if there are lots of locally acyclic cluster algebras. Good news, there are. So some families of locally acyclic cluster algebras. Cluster algebras of most marked surfaces, these are the ones corresponding to rectangular spaces. They just need to have some stuff happening on the boundary. Cluster algebras of Grassmannians, flag varieties, and positroid varieties are locally acyclic. And a recent result here was by a number of folks, not even gonna try, are Bott-Samuelson varieties, kind of a generalization of Richardson varieties, and a generalization of those called braid varieties. So lots of interesting and large families of cluster algebras, specifically those that exhibit nice properties, are known to be locally acyclic. Now's where Karen enters the story, right? We've seen a lot of fun history of cluster algebras in the aughts. But I met Karen at MSRI in 2012. There was, they organized a thematic semester at MSRI that was on cluster algebras and commutative algebra. So Sergei Fomin and Zelevinsky had introduced cluster algebras, and there was a lot of questions about their commutative algebraic properties. So there was this joint workshop, which was mostly separate, but there was a sense that, oh, maybe we'll find some common ground.
Two thematic semesters.
Yeah, okay, right. There was a joint workshop and two separate.
Try to get us talking to each other.
Yes, that's what I was trying to remember. Yes, the workshop was joint, the thematic semesters were separate. And so yes, there was a joint workshop which I went to. It was a really kind of amazing workshop. I recommend you go, but according to the website, the registration deadline has passed. But on that first day, Karen and Sergei both gave talks. Karen talked about F regularity, and she put up a big list of a bunch of F regular algebras, strongly F regular algebras. And Sergei gave a talk about cluster algebras, and he put up a list of a bunch of cluster algebras. And it did not go unremarked at the time, but they were basically the same list, which led to the natural question, are cluster algebras strongly F regular? Now, of course, the answer is, in full generality, no, they couldn't be. I've already given you an example of a horrible, that horrible Markov cluster algebra, which is also, doesn't plays very badly with the Frobenius. But we again have this dichotomy. The nice cluster algebras appear to be strongly F regular, but not every cluster algebra is strongly F regular. Okay? And so Karen and Sergei got to talking. As a precocious postdoc, I inserted myself because I was like, hey, I've got this cool thing called locally acyclic cluster algebras. I think we might be able to show that they're strongly F regular. So Karen and I got to talking. That eventually led to her bringing me to Ann Arbor for a postdoc, which changed my life in immeasurable ways. I think if there's one thing I think everybody would agree about Karen, that she's quite a force of nature when it comes to entering your life and stimulating math and just sort of, things are substantially different afterwards. So yes, quite a bit came out of this curious workshop where I met Karen, and we all realized, hey, there's something there. The most obvious thing that came out of that was a collaboration. We later added on 2 more postdocs of Karen's, and Helga Bonino and Jenna Ratchcott. And we showed that if a cluster algebra is locally acyclic, then over any F-finite field, it is strongly upregulated. And as a consequence, we just induce up to an algebraically closed field of characteristic 0, we have at worst canonical singularities. Okay? I think we're using normality in here as well. But that's true because it's locally acyclic, so we're good. So this sort of resolved the question that came up at Karen and Sergey's parallel talks. And also gives us a nice bound on how bad singularities of cluster algebras can be, even in the characteristic 0 case, even over, say, the complex numbers, right? And I've always really loved this result. I remember as a grad student learning that you could prove things in algebraic geometry, even over the complex numbers, by showing them over enough primes and positive characteristic. I was always fascinated by that. So I feel very privileged to have a result that fits into that grand tradition of, like, if you want to know a question over the complex numbers, study it over enough primes. While we're talking about how bad singularities can be, it's literally the name of the conference, it's worth reiterating that the Markov cluster algebra, as my running example of a bad algebra, it's non-Noetherian, but in fact, all of its non-Noetherianness is concentrated in a single singular point. There's a single point whose defining ideal is its own square, which is bad for a lot of ways, but it's definitely not Noetherian. Okay, so we see that locally acyclic cluster algebras have very nice singularities when they have singularities at all, but arbitrary cluster algebras can be quite bad. While we're here, I want to mention a result that's quite a bit more technical, but I kind of love it because it goes the other way. Okay? My result with Karen had to do with looking over enough primes, in positive characteristic, and deducing geometric results in complex numbers. Here's a result by Lamb and Spire that goes the other way. It uses the geometry of locally acyclic cluster algebras over the complex numbers to deduce positive characteristic results. The results are quite technical. They study, essentially what they do is they consider locally acyclic cluster algebras that have an additional condition called full rank. That just means an associated matrix has the largest possible rank. It's easy to check and very common. But they use it to essentially construct the complex cohomology of the cluster variety, and then use comparison theorems to deduce facts about the Étale cohomology of the FP bar points. Here's a bunch. I will now try to elaborate on these. But essentially, the Hodge structure of that cohomology is very nice. It splits completely. And as a consequence, the number of points over any finite field is particularly well behaved. Okay? And so one manifestation of that is that the number of points over a field of order Q is given by the value of some fixed polynomial at Q for Q large enough. That is, the number of points over a field of order Q is asymptotically polynomial in Q. And in fact, for most cluster algebras, it's true for all Q and not just large enough Q. So this is not really a result I want to talk about too much, but I just really love that it goes the other way. The complex geometry of the cluster algebras now informs the positive characteristic geometry, the number of points. I should say this result has found its purchase in several applications. Subsequent results by Galoshin and Lamb enumerated number of points in positroids in positive characteristic, which went on to enumerate friezes and number of friezes in positive characteristic. So there's lots of applications of this, and I should say you can explicitly get this polynomial by studying the cohomology carefully, which we definitely won't do, but there's a whole box here that is cool for studying positive characteristic. Instead, what I like to do is I like to study not positive characteristic, but positive geometry. And I really mean the positive real numbers. Okay? This is a sort of semi-algebraic question that doesn't even make sense in most varieties, but because of the extra structure the cluster algebras have, we can make coherent sense of things like the positive real points. Okay? And to do this, let me elaborate on what might feel like a slight strengthening of the Laurent phenomenon that nevertheless was the big open conjecture in cluster algebras for 15 years, basically. So we already know that every cluster variable is a Laurent polynomial with integer coefficients. Turns out those integers are always positive. Very tantalizing fact, before it was proven, because you really want those integers to count something. And in examples, it's easy to find all sorts of interesting counting problems that count the coefficients in certain things. Things like sub-representations, domino tile, and tropical curves. Whole areas of cluster algebras came about because people were desperately trying to find interesting counting problems enumerated by these coefficients that work sometimes and therefore verify positivity in those cases, but that didn't extend to all. Ultimately, this was shown in 2015 by a pair of groups. Lee and Schiffler just did sort of a very long argument. And then Grosheck and Kielin-Katsevich realized this is a consequence of a bigger structure following from some mirror symmetry I may mention at the end. So both very interesting proofs of this result, but we now know that these coefficients are always positive in use. Okay. Right. And actually, it's worth remarking that why that isn't obvious, right? Because our mutation formula only ever has addition in it. But it is possible to give a ratio of two screw this up. A ratio of two positive polynomials that is a Laurent, but is not itself positive. Right? So this kind of phenomenon never occurs. Okay. So what can we do with this? So let's start by just kind of finding the totally positive points of our cluster variety. So basically from now on, we're going to be working the real points of the cluster variety, which we've already been looking at, but that's where we can talk about inequalities like positivity. And I'm going to look for points where every cluster variable is positive. Okay? But the positivity theorem says that if that initial cluster has positive values, well, every other cluster variable can be gotten by just plugging those positive numbers into a positive Laurent polynomial. And plugging positive real numbers into a positive Laurent polynomial never gives you a negative number, right? It's just addition, multiplication, and division. None of those make you negative. So from the positivity theorem, we get that each cluster gives you a certificate of positivity by itself. If x1 through xn are positive at P, then every cluster variable is positive at P. There's lots of redundancy in the positivity there. Okay? And the historicity is a little bit backwards. This is actually this total positivity criterion business was really the first justification of cluster algebras. This is one of the things that got people excited in the first place, because all those examples I gave before, the Lie groups, Grassmannians, decorated type Muller spaces, the positive parts were interesting subsets people already wanted to study. And the fact that each cluster gave you a subset of the special functions that were the only ones you had to check to verify you were totally positive was an interesting application, right? So for example, if you give me an n by m matrix and you want me to check if every minor of that has positive determinant, I can give you a much smaller set of minors to check to show that the determinants are all positive. That was an early application of cluster algebras. Okay, but what does this total positive region actually look like? Well, it's where a cluster has positive values, but we already know where it has non-negative values, non-zero values, is an algebraic torus. Okay, so the places where it's positive is just going to be unorthoed inside that space, right? So in our example, here we've got that two-dimensional algebraic torus, and the totally positive region is just this quadrant here, right? Where both coordinates are positive. Now there's sort of two obvious cluster variables, x1 and x2, and then there's three less obvious cluster variables. But positivity says those other three are always positive on this region. So the positivity of two of them gives the positivity of all five. Okay, so kind of the point of this is the totally positive region is boring, and it's interesting that it's boring. It's always contractible, it's always semi-algebraically isomorphic to a positive orthant. Okay? And in fact, in many of the applications, it's an interesting theorem that the total positive region is contractible. All right, but let's ask questions that have interesting answers, not just positive orthants. Okay? So, all right, we got a lot of fun asking where the cluster variables have positive real values. Let's ask where they have positive integral values. Make this a Diophantine question. Okay? So a point in the real cluster variety in which every cluster variable is a positive integer is called a frieze point. I don't really love this name, but it comes from friezes, which are a whole field that I don't have time to get into. But friezes are, roughly speaking, various configurations of positive integers satisfying certain identities. I'll give one example on the next slide, but there's all sorts of different kinds of friezes that people study. And a reoccurring theme is many different types of friezes are now known to be in bijection to frieze points in certain cluster varieties. Okay? So if you're in the business of asking how many friezes there are of a certain type, if you can show that they correspond to frieze points in the cluster variety, now you're asking how many frieze points are there in the cluster variety. Okay? So this leads to questions about finiteness and enumeration of frieze points. Okay? Here we go. Let's see an example. So the simplest kind of frieze is called the Coxeter-Conway frieze. This is the example, the type of frieze that sort of set the field off. And what Coxeter-Conway frieze is just going to be an infinite strip of positive integers, offset in this kind of diamond pattern, such that the top and bottom rows are consist entirely of ones. And then the important condition, every 2 by 2 diamond has determinant 1 if you rotate your head 45 degrees. So for example, here, 2 times 2 minus 1 times 3 is 1. A little math for you there. And 3 times 1 minus 2 times 1 is 1. Okay? So that I assert is true for every 2 by 2 diamond. Okay? Now in this case, it's a pretty simple problem, but if you get taller and taller friezes, you get quite interesting configurations of numbers. Interesting enough, the Coxeter and Conway wrote a couple of papers on them. But a fact that we now know, decades later than when Coxeter and Conway studied them, is such friezes are in bijection with frieze points in these quivers of paths, quivers of type AN. Okay? So for example, Coxeter-Conway friezes of height 4 are in bijection with frieze points in our running example. Points in this picture here, where all 5 cluster variables have positive integer values. Now I'll save you the work. There are 5 such points. Here's 1, 1, here's 2, 1, here's 1, 2, 2, 3, 3, 2. Those are the only points at which all 5 cluster variables are positive integers. Okay? Now we get these 5 guys, we translate back. This tells us there are 5 Coxeter-Conway friezes of height 4. Okay? The historicity here is a little bit backwards. Coxeter and Conway counted these by identifying them with triangulations. Hence, they're counted by Kaplan numbers. Frieze points in these guys are also counted by Kaplan numbers. So if you actually put my feet to the fire, this is just 2 things that are both counted by the Kaplan numbers. But in other examples outside of Coxeter-Conway frieze, this correspondence still holds, where there aren't nice combinatorial formulas that count 100 different things. Okay. So, as I mentioned, the finiteness of frieze points was an open question for many years. And so to attack the finiteness of frieze points, you could do something kind of fun. So far we've asked where all the cluster variables are positive real numbers. And we've asked where all the cluster variables are positive integers. But every positive integer is also greater than or equal to 1. So let's split the difference. Let's consider points where every cluster variable is a real number that is greater than or equal to 1. Okay? We call these superunitary points, literally greater than 1, but it sounds more cool than it is. And this is nothing but considering the subset of your totally positive region, which is carved out by setting every cluster variable greater than or equal to 1. Remember, this guy has 5 cluster variables. If we set each of them greater than or equal to 1, we get 4 lines and 1 hyperbola, which carve out this almost pentagonal region. It's a topological pentagon. Okay? But a couple of things here. It's almost a pentagon. I mean, it's homeomorphic to a pentagon. It also has the frieze points exactly at the corners. And of course, the frieze points are in there. The friezes are where the cluster variables are positive integers, and every positive integer is a real number that's greater than 1. But the superunitary region has is a topological space, right? It's continuous, so we can talk about its topology, and rather than just its
Why not
enumeration.
just consider the convex hull of the friezes?
That's a great question. Why don't we consider the convex hull of the friezes? The reason is because that depends on the initial cluster. Okay? So here I picked an initial cluster and embedded it based on that. And so there you're seeing an obvious version of convex hull there. But if I picked a different cluster to be the initial one, this region here translates over there, and the superunitary region is independent of a choice of initial cluster, but the convex hull isn't. And in fact, it is still an open question whether this region is always contained in its convex hull. Be cool if we knew that, but that is, as far as I can tell, a difficult question. Okay. Okay. What we do know is how to generalize this for other finite type cluster algebras. Me and my postdoc Emily Gunawan showed that for finite type cluster algebras, the superunitary region is always a polytope in the sense that it has a homeomorphism to a topological polytope. Already we see it can't be a polytope on the nose, it's got a curved concave wall there, but topologically it's a polytope. It has the face structure of a polytope, and each of those faces is homeomorphic to a ball. Okay? So in general, this is true in the finite type world. The superunitary region is always homeomorphic to a specific polytope called the generalized associahedron. So in fact, for AN, for these path quivers, we get the on-the-nose associahedron, if you know what that is. For other guys, you can get the cyclohedron or the simplicia. I don't even remember how it looks like, but various associahedra that encode some interesting combinatorics. We have a far more germane application in mind. We care that polytopes are compact, right? So here, I've got a compact region, and I know the Frieze points are a discrete set inside here. But a discrete subset of a compact set is always finite, right? So a weird but immediate consequence of this is that every cluster algebra with finitely many Frieze points must have, every cluster algebra with finitely many clusters, that is finite type, has finitely many Frieze points. Okay? This is an open conjecture for several years because in the language of Friezes, it was asking whether there were finitely many Dinkin Friezes, okay? Which is now known. And I should say this is if and only if your cluster algebra has infinitely many clusters, it also has infinitely many Frieze points. Okay, so that was a fun result. And I think that's pretty much all I have time to talk about. Yep. I had a big long list of stuff to talk about and I excised most of it, but one thing I did want to mention, just because I think a lot of the words excite people in the audience, and it's one of the things that excites me most about the future of cluster algebras, is the connection with mirror symmetry. So smooth cluster varieties are what are called log Calabi-Yau. Calabi-Yau varieties are varieties with trivial canonical bundle. And the log Calabi-Yau ones are ones that need not be projective varieties, but that can be realized as the complement of a simple normal crossing canonical divisor in some projective variety. So for example, if I take projective space and I take the axes in there, that's a simple normal crossing canonical divisor, and if I cut it out, I'm left with an algebraic torus. Okay. So those are log Calabi-Yau. And so the Gross-Seibert program is sort of one of the branches of mirror symmetry that is trying to generalize a lot of the results of mirror symmetry from Calabi-Yau varieties to log Calabi-Yau varieties. An important prediction there, which we basically know exactly how it works, a lot of the explicit computations are done, is a cluster variety should come in mirror pairs, x and x check, such that the boundary divisors on one parameterize a canonical basis of functions on the other. And which contains, among other things, the cluster variables. So this is really saying that the special cluster variables as functions on here are really just the tip of the iceberg of this canonical basis of beta functions coming from this mirror symmetry construction. Okay.
So whose result is that? That they are log Calabi-Yau?
This is Gross-Hack and Kiel and Kinsevich. Yeah. I guess it's an earlier paper, Gross-Hack and Kiel, that they are log Calabi-Yau. The construction of this basis parameterized by the boundary divisors is in a seminal paper of Gross-Hack and Kiel and Kinsevich. But yes, Gross-Hack and Kiel is the names you're looking for. But this means many algebraic problems of X can be translated into topological problems on the mirror and vice versa. For example, I mentioned that many of the interesting examples of cluster varieties actually are stratified by cluster varieties. They have one big dense one and then a bunch of pieces in the boundary. And now through this mirror construction, we're seeing that on the dual, we have this affine space. And if we look at an appropriately convex polytope in that dual, much in the way that a polytope determines a compactification of a toric variety, this sort of broken line convex polytope in the dual determines the compactification of a cluster variety. Okay? So we're seeing sort of all the tools of toric varieties generalizing to this world. Okay? Love to talk about it, don't have time. Instead, the point of this talk was to get you excited about cluster algebras, so it would be cruel of me not to tell you what to do next. So instead, I'll give you somewhere to go next if I've sufficiently whet your appetite. A good starting point, I mean, First things due is an apology. It's just not a very well documented field. A lot of seminal results are sort of in the corner of one paper somewhere. I think that's true for a lot of fields, but I feel it particularly bad in mine. But Fomin and Zelevinsky and Williams have been working on a textbook for many years, the first 7 of which are available in the archive. They're quite good. And then if you're looking for other points of entry, kind of a curious one, if you're an algebraic geometer, which many of you probably identify yourselves as, I would recommend as a starting point, counterintuitively, cluster algebras 3. There's a series of 4 papers, cluster algebras 1, 2, 3, and 4. They're all very good in their own way, but counterintuitively, number 3 is the most accessible and also has the most algebraic and geometric results. It's maybe my favorite paper. If you're more of a representation theorist, which sure, Bernard Keller has some great notes. I recommend cluster algebras and cluster categories. And if you're interested in topology, either things like tight Muller space or things like skein algebras and knot theory, I recommend cluster algebras and triangulated surfaces by Fomin, Shapiro, and Thurston. And I think I'll stop there. Yes.
Can you go back to the pentagon for a moment?
Absolutely.
That curved part.
Mhm.
Do you know the degree of the defining equation?
Yeah, it's hyperbola.
Okay.
Yeah, this is, so all I'm doing is I'm taking every cluster variable and setting it greater than or equal to 1. Clear, yeah, multiply over, move over. Hyperbola. Yeah, good question though. Yes.
So, do you have any easy example of a cluster variety that has like an isolated midpoint, but it's not singular, it's special?
Sure. Yes.
Repeat the question, Greg, I didn't hear it.
The question is, do I have a good example of a cluster variety that has a deep point that is not singular? That is smooth. So, yes. Honestly, the biggest obstacle is that there's lots of variants of cluster algebras, and I didn't give you all of them. So the easiest way to construct them is by using frozen variables. A frozen variable is just where you declare a vertex to be forbidden to mutate. So if I consider this quiver, and I say, you can't mutate that last guy. But if I have a frozen variable, the convention is you also throw the inverse to that frozen variable into the cluster algebra. Now this only has 2 cluster variables, well, 2 mutable ones. This is x2 plus, mutate here, then mutate back, that's it. Then it has this. Let's call this x1 prime. So this is the cluster algebra. So right away you see that you can eliminate x2. So this is isomorphic to x1, x2. But then I need, x1 prime. But I still need the x2 to be invertible, but x2 is now equal to x1 prime minus 1. So I localize this by just adding a formal inverse to this. Okay. So this presentation makes it clear that this cluster variety is just the complement of a hyperbola. Okay. Now this has 2 clusters, so it has 2 cluster tori. And the cluster tori where x2 is not 0, but that's also so x1 and x2 are not 0. So that's going to be, well, not on this line, which nobody's 0, and not x1 is not 0. So the complement of the cluster, one cluster tori is the complement of this axis. The other cluster tori is the complement of this axis. So the unique deep point is the origin. So that's the simplest example of a cluster algebra or cluster variety with a deep point that is, of course, non-singular.
Because they're infinite.
Yeah, exactly. But there's more sophisticated examples. There's, in a sense, if you take any cluster algebra with singular, any locally acyclic cluster algebra with deep points, if you add enough frozen variables to that, those deep points will still persist, but they will become smooth. They'll be embedded in a larger cluster variety, and while they're singular in the slice that restricts the original guy, they're smooth in the bigger space. So, yeah. Yes.
Maybe I got it wrong, but you mentioned this result about this classification of when the AN thinking diagram has, or that has.
Yep.
Points. What about the other thinking diagrams? Is it known or?
Yes, so Dicke diagrams are finite type. So those are in, well, some of them are in my paper with James Beyer. We did A and D, he did the rest in his thesis. So yes. The answer is similarly unsatisfying. I think Bn has none. I think Cn has some, but again, up to some modular criterion. E7 has some, E8 doesn't, stuff like that. So they're capricious and unpredictable. Yes, Javier.
So are all cluster algebra the cluster varieties blow-ups of canonical varieties?
That's a great question. The answer is no. So you're asking to what extent this construction generalizes? So this appeared wrong in print in a paper of Gross, Hacking, and Kiel. Said it was always true. It's not. If your cluster algebra is, well, here, let's do it in a couple of ways. If your cluster algebra is full rank, then this is always true for the upper cluster algebra, something I did not define. And then many cluster algebras coincide with their upper cluster algebra, such as every locally acyclic cluster algebra, and then this becomes this is the cluster variety. So this gives you a construction that gives you every full rank upper cluster variety, and then those are often equal to cluster varieties. But no, this is not always true, because this will never give you a singularity, I don't believe. So already you see that any singular cluster variety can be constructed in this way. Yes.
So you mentioned this low-Calabi-Yau thing. Do you know? Does it mean that the projective variety is final, or is it original? So, or actually, a related question that may be easier to answer: is it true that cluster varieties are unirational?
Or what?
Unirational.
They're rational.
They're rational.
I think they're rational, right?
Yeah, they got it out. They
Their
got it
function
open
field
torus.
is just.
All right. Yes. Yeah.
Yeah.
Okay. And compliance, you mean the support of the canonical?
Yes, exactly.
Because it's negative.
Or maybe I mean anti-canonical advisor.
Yeah.
Okay. Yes. Yeah. So whatever the axes in Pn are,
Right.
that's what I'm looking at. Yes.
Is there a geometrical intuition behind the way that you define the mutation?
The closest probably has to do with this blow up picture, which means it's not always valid, but it's valid like up to codimension 2, for example.
What was the question? Sorry.
Is there a geometric interpretation of mutation? So what I would say is that so if you're in one of these cluster tori and you want to get to another cluster tori, you can always do that by one of these blowups at infinity. So you can always blow up some locus in the boundary and cut out the exceptional divisor of the boundary, and then find another torus in there whose coordinates are precisely the mutated, the original cluster variables plus the mutated one. So so I think that's as close as there is to a geometric interpretation of mutation. It's a very specific kind of blow up and then blow down kind of thing. Yeah, no problem.
Maybe I'll ask-
kind of,
Oh, sorry, go ahead.
so following up with Jan, question over there. So Calabi-Yau, log Calabi-Yau, should I understand of these cluster varieties? Suppose I can classify the panel varieties, and then there I look for the rational ones. Are those the cluster varieties?
I mean, cluster varieties can get very complicated. And I guess the first thing I should say is when we're doing this, we're working up to codimension 2. So these results are all sort of up to codimension 2 because cluster algebras can be quite bad. Well, I mean, here I've assumed smooth, but all of these papers are sort of implicitly working up to codimension 2. So already that's sort of an issue. I mean, I think the ones they're working with are precisely the ones that can be constructed by this blow-up construction, where you just take, you just take an affine space, you blow up some locus on this divisor, and then you cut off that divisor. So that's how you show their log Calabi-Yau. You just show that because algebraic tori are log Calabi-Yau, this blowing up procedure doesn't break whether you're log Calabi-Yau. So yeah.
Can I restate your question? And it's not quite the same, but I think one question would be, if you have a Fomin variety, which is rational, and you remove an anti-canonical divisor, or maybe it needs to be normal crossings one or something, does that always have a cluster structure?
Yes, the answer to that is no. It is not true. The equivalence doesn't go the other way. You can find, so you can take a Fano and then find a particular normal representative of the canonical divisor with simple normal crossings and cut that out, and that will be log Calabi-Yau. And some cluster varieties can be realized that way. I believe the characterization is that these guys come in mirror pairs. And you need the mirror to have not just simple normal crossings, but it needs to have at least one point with a dimension 0 stratum. You need enough different divisors meeting to where they reach codimension 0. Because each of those divisors is going to represent a cluster variable in the dual, and then the fact that there's that you have dimension many of them meeting there is giving you a full cluster worth of functions on the other side. So this is how Groshacky and Kiel sort of see the cluster structure emerging from this mirror symmetry picture. Divisors give you nice functions on the other side, and when they meet in a simple normal crossing is when they're compatible. And so if you have dimension many of them, you get cluster on the other side. So that is the expected correspondence. But it's quite special. You need a Fano, you need a canonical divisor with simple normal crossings, and then you furthermore need that one of the two guys goes all the way down to 0 dimension.
And it better be rational.
Yes, for sure. Yes, for sure. I think it is. My vague recollection is that if you have a 0 stratum, you are rational. Yeah.
Okay.
At least Sean has asserted that. He's sometimes wrong.
Sean asserts a lot of stuff.
Yes.
Talk about force of nature.
Different one.
So in non-smooth case, do you have like any nice compactification of the cluster varieties?
I would say the answer is basically yes. So a whole big area of the field I didn't get a chance to talk about is that cluster algebras essentially have a nice basis with positive structure coefficients, much like the basis of nomials. And so by picking cones inside that, I mentioned this a little bit with polygon, but picking cones inside that basis, you can parameterize compactifications. So there's a whole lovely theory about how to compactify cluster varieties, even in the non-smooth case. Yeah, smoothness is not necessary there. If your algebra and your cluster algebra are different, there's some issues, but let's ignore that.
I want to ask about this speculation that we were having. It might have been mostly with Angelica, but whether there's sort of a cluster way to resolve the singularities of a cluster algebra.
Mm-hmm.
Do you know what I'm talking about? Because it looks like there would be some natural way to pick a thing to blow up. And did you ever think about that? Sort of.
So I can tell one thing, which is sort of which leads you to believe that something like that might be true. So for example, I told you that the Markov cluster algebra has a very bad singularity, but the Markov cluster algebra embeds inside the Markov upper cluster algebra. So remember that cluster algebra is contained in many different Laurent rings. So you can intersect all those Laurent rings. This is called the upper cluster algebra. And the Markov upper cluster algebra is just a hypersurface. It's a three-dimensional hypersurface. It's very nice. And it has 7 deep lines. I guess I need to assume algebraically closed characteristic, not 2, where the number is slightly different. If you blow down one of these affine lines, which is something you should never do, but if you do it, you get the Markov cluster variety. And so that non-Noetherian singularity is what happens when you blew down one of those lines. So in this particular example, you get a lovely resolution by passing from cluster algebra to the upper cluster algebra. However, upper cluster algebras can be quite bad. Whether there's some so here we'd never left the world of affine varieties. A perfectly reasonable question, which I think is sort of what you're feeling towards, is whether there's maybe a non-affine way to fix the singularities even when the upper cluster algebra is bad. Could be. Feels like there should be. Something I can say is that in the world of cluster varieties I mentioned, if you're locally acyclic, you can always add enough frozen variables to be smooth. So that means your cluster variety will be a slice inside a smooth cluster algebra, cluster variety. So that's not a resolution of singularities, but it's sort of dual form.
More questions?
Thank you so much.